In the 18th century, the scientific world believed heat was a physical substance. They called it caloric, an invisible, weightless fluid that filled the pores of matter. According to this theory, heat moved between objects like water flowing between two tanks until their levels, or temperatures, reached a state of equilibrium. This fluid theory was challenged in 1798 by Benjamin Thompson, also known as Count Rumford. While supervising the boring of a brass cannon, Thompson noticed something that the caloric theory couldn't explain. If heat were a fluid trapped in the metal, a sharp drill should release more of it. But Thompson observed that a dull drill, which required far more mechanical effort to turn, generated enough heat to boil water. The heat produced was directly proportional to the work done by the horses turning the drill, not the amount of metal removed. This realization paved the way for the Industrial Revolution. If mechanical work could be converted into heat, then the reverse was also possible. By harvesting the heat from steam, engineers could move pistons, rotate wheels, and propel entire trains across continents. Heat was finally understood as energy in transit. It is not a stagnant fluid, but a mode of energy transfer that can be manipulated to move the world. Today, most people assume that adding heat to a gas simply makes it hotter, but that is only half of the physical reality. Imagine a sealed cylinder filled with gas and capped by a heavy, movable piston. As energy enters from below, it doesn't remain a unified force. The incoming energy fractures into two distinct roles. One portion drives molecular agitation, increasing the random speed of the gas molecules. The remaining energy portion provides the physical thrust required to lift the heavy weight of the piston against gravity. Adding heat forces the energy to choose between two paths. It either increases the internal chaos of the system, or it performs external mechanical labor. To track this energy split, we use three variables. First, heat supplied to the system is delta Q. Next, internal energy change, delta U, represents molecular kinetic and potential energies. Finally, work done by the system displacing the piston is delta W. When we combine these, we get a foundational law of nature. The heat supplied to a system must equal the change in its internal energy plus the work it performs. In a laboratory setting, calculating that mechanical work, the delta W, requires us to look at the physical dimensions of the cylinder. Work is the result of a force moving across a distance. For the gas, that force is the internal pressure acting against the piston's surface area. Since pressure times area is force and area times distance is volume, work is defined as pressure times change in volume, or P times delta V. This updates the first law into a practical form. Delta Q equals delta U plus P delta V. This relationship dictates that whenever a thermodynamic system expands, it must pay a mechanical energy tax to the universe to clear its own path. To understand why this law is so resilient, we can compare two different ways of reaching the exact same physical state. In path 1, we supply a high amount of heat while allowing the piston to move. The gas expands significantly, meaning the system performs a large amount of work. In path 2, we lock the piston so no expansion is possible. We then supply only the minimum heat needed to reach our final temperature. In this scenario, the work done is 0. This pressure-volume chart shows these two divergent routes. While both paths start and end at the same points, the journey between them is different. In thermodynamics, the amount of work done is the area under the curve. Because these curves differ, the actual amounts of heat and work involved depend entirely on the specific path the system takes. However, if we rearrange the first law to isolate the internal energy, a hidden constant emerges. Delta U equals delta Q minus delta W. When we look at path 1, the high heat and high work cancel out to a specific value. In path 2, the low heat and 0 work result in that exact same number. Even though the path variables changed, their difference remained identical. This proves that internal energy is a state variable. It doesn't matter how a system arrives at its destination, it only cares where it is. This fixed internal energy serves as the immutable core of the first law of thermodynamics.